It's like I've had all the math teachers I've had.
What we're going to look at here is chapter 5, section 4. We're going to review a couple of sections in chapter 5. So we're going to do chapter 5, section 4, 5, and 6. That'll get our brains rolling because you should have gotten that far in calculus 1. So chapter 5, section 4. The fundamental theorem of calculus, which is interesting because it waited till the very last chapter of calculus 1 to tell you what the fundamental theorem is. And basically, what the fundamental theorem of calculus is with the integral. And that's the fundamental theorem of calculus is, and what it means. What does the integral mean?
The integral of f of x of dx is equal to f of b minus f of x.
But what does it mean? This is the formula.
So the integral of any function is equal to whatever the difference between b and a is.
And then what does that find for you?
The area under the curve.
Very good.
Between b and a.
Area under f of x on the interval AB. It's the area under the curve. And that is what Leibniz and Newton were looking for when they had the big competition back in the 1700s or 1800s. That was what they were looking for, because what the whole purpose of trying to discover calculus was to determine the volume of any object, so it helped in shipment and transport. Because the shape of a ship looks like this. If you're looking at on the beam, it's not a perfect square. So how much stuff can you put in there? And that all depends on how much area or volume is in the object. So this is the fundamental theorem of calculus. To determine this, how about the mean value theorem? What does the mean value theorem tell us?
I don't remember that.
Okay, the mean value theorem, that's on your sheet. It's theorem theorem 3. It's pretty interesting actually what this thing finds. What the mean value theorem finds is this. You have any function f of x on an interval AB, on a closed interval AB, let's just, see. What it says here is this. There is a C somewhere between A and B. It's contained inside the interval AB. It's the average of the function. What it's saying is this. The horizontal line, the rectangle formed by drawing a horizontal line through C, the area of that rectangle is equal to the area under the curve f of x from A to B. Now, it means it's a pretty impressive discovery, because if we didn't, then we'd have to look at the function using the Riemann sums and separating these in smaller intervals. So the mean value theorem helps us determine that geometrically a lot faster. So this height here at f of c gives us the same area as under the curve f of x between a and b. So let's look at the first example. Here's the first example. Show that if f is continuous on AB and a doesn't equal b, and if the integral from a to b of f of x equals dx is equal to 0, then f of x equals 0 at least once in the interval. So how do we do that? Show that if f is continuous, remember, if the fundamental theorem of calculus, actually almost all of the theorems that we state say that f of x, f has to be a continuous function. Why is that important?
Well, it has to be a continuous function between a and b, or just
Well, okay, between an interval a b, yeah.
The reason it needs to be continuous is that if there's like a infinite discontinuity or anything like that, would you not get it?
Yeah, it wouldn't exist, right?
Yeah.
And then so we have to only, if you have a discontinuity, if you have a jump discontinuity, then you have to separate the function into different domains.
Okay.
So, but for this level, we'll look at all functions have to be continuous,
Okay.
and not just in the a b, which means the entire function is continuous. So how do we figure out this, answer this question? Show that if f is continuous on a b and a doesn't equal b, and if the integral equals 0, then f of x equals 0 at least once in that function. So how would we do that? I'll give you a clue. It's right there. What we have to use.
You have to divide, basically like divide the function.
Well, we have to use the mean value theorem, and then we'll discuss what that means in a second. But yes, so we'll use the mean value theorem. So we have the average of f of x is equal to 1 over b minus a to b, f of x dx. Since a doesn't equal b, this is defined. We have 1 over b minus a. It says if the integral is equal to 0, that means this is equal to 0, then it equals 0. So now, we have to move around. Oh, no. Is there a button on there?
I think that one just turns off the light.
Yeah, it does. I was sitting here.
Sensor tips. Okay.
So, and there you have it. That proves it. That then f of x has to be 0 at least one place. In order for this to be 0, the endpoints can't be 0. So that means this interval has to have a 0 in there because it has to equal 0. Now, how do we prove that? When will that happen? A to B to C. Let's look at the cosine curve or a sine curve from 0 to pi to 2 pi. We're looking on the interval from 0 to 2 pi. So we have 1 over 2 pi minus 0. The integral of sine x dx. In order for this to equal 0, okay, this goes on to a little bit more deeper meaning. We know that the coefficient is not 0 because a doesn't equal b, so it can't be 0. So that means this function, this integral has to equal 0. When can the integral equal 0? Well, in this case, we have integral of sine is negative cosine from 0 to 2 pi. So we have negative cosine 2 pi minus negative cosine 0. Cosine 2 pi is 1 minus negative makes it a positive. Cosine of 0 is 1. So what does this tell us? The only way an integral can be equal to 0 is if the areas are equal but opposite. In order for that to happen, you have to have at least one location. This is the value, this is the C point, where f of C is equal to 0. So the only way an integral can be equal to 0 is if you have equal area above the x-axis and equal area below the x-axis. And the only way that happens is it has to cross the x-axis at least one point. Make sense?
Mhm.
That's that one. Now, fundamental theorem of calculus, the first part states this. And I included the theorem somewhere. Well, there's an example of it right here. In order for the integral to be equal to 0, that means the area above it has to equal the area below it. And if that's the case, that means there has to be at least one place where the function crosses the x-axis. So the first part. We're used to this function here. F of x, capital F of x equals the integral from a to x of f of t dt. Also notice that one of our bounds of integration is our variable, is the x value, is the independent variable. What this function finds for, you have all this stuff already on your sheet, don't you?
Yeah, I just like
Yeah.
writing it down.
Okay. It says here, the variable x is the upper limit of integration and the integral. Why? What does that mean? It tells us that our bound, the closed interval, can move. So it's not fixed to any one point. It goes from a to some value x. And that leads to our formula f of x plus h minus f of x over h. What is this formula called?
Okay, so difference quotient.
And where did it come from? Because it's the area of this f of x function is some part. Take away some other part, the f of x part, and what you're left with is the part with the function you're looking for. Okay, all this stuff is just basic rudimentary. It goes from the how we use the integrals. Actually, I really shouldn't put all that stuff in there. There's just a lot of extra stuff I don't even need it in there. What's important are these. You have the theorem. Now use this theorem, the part one theorem of calculus, to solve these four problems. Right, so we have example 2. Use the fundamental theorem of calculus to find dy dx. A. Y is equal to the integral a to x t cubed plus 1 dt. So how do we solve that?
So wouldn't we start off by taking the integral of the function inside?
Okay. Remember, we're looking for use the find dy dx. Yeah, because we're looking for dy dx. What that means is we're looking for dy dx, which means we're taking the derivative of this function. So what's that going to equal?
Uh, well, wouldn't it be the same thing?
Because this integral and the derivative pretty much cancel each other out.
Yeah.
And so we're just putting it with respect to x. Because anything that has dA is a constant, it would disappear. So let's look at what you said earlier. So we're taking the derivative of this integral. If we took the integral of this function first, we would get t to the 4th over 4 plus t.
And you would plug in your bounds.
What, yeah, we have to get the derivative of this function. So we'd get x to the 4th over 4 plus x minus a to the 4th over 4 plus a. So we get x to the 4th over 4 plus x minus a to the 4th over 4 plus a. So, yeah, that's what we just did with the integral. Now we're taking the derivative of it with respect to x. So this one would be 4x to the third over 4 plus 1 minus 0, because these are constants, they would go to 0. So this would give us x cubed plus 1. That's where it came from. And what does that show us? Is that the integrals and derivatives are inverses of each other. Okay, so let's look at B. Example 2B. That one's the same thing. We have to find using the fundamental. 3t sine t dt. Okay, so go ahead and work that one out. First off, remember, look at the formula. We have to use this formula. Is this set up the same way? Look at the bounds of integration.
Would be set the opposite.
So what do we have to do first? We have to change the bounds of integration. And when you do that, what happens to the function itself?
It becomes,
Negative.
yeah. Or basically you just add a -1 to the whole function
Multiply negative 1.
times -1.
Yeah. So we're looking for dy dx. And that negative can come out in front. This negative stays out in front. Pretty much, since this is a constant, we don't have to worry about the bottom, the a part, because that's going to be 3a sine 3/5 sine 5. So these are constants. These will disappear. All we'll have left is and there's dy dx. Draw that one? Because yeah, the constants will just disappear when we take the derivative of it. Example 2c. Y is equal to 1 to x squared cosine t dt. Remember, we have to use the same formula. Do we have the same bounds of integration? No, that's
Or-
x squared.
okay.
So how do we fix that?
Q square or cube or not cube, square root it.
No, let's make it use the substitution method. So now we have our bounds of integration. So u is a function of x. Now we have to use the chain rule. Remember the chain rule?
Mhm.
dy du times du dx. That's the chain rule. So dy dx becomes d du of our function. Oops, let's first do this. Of our function 1 to u cosine t dt times du dt. Or dx, I'm sorry. We have to get du dx there. So dy dx what's this one going to be?
Would it be cosine or not cosine sine of u?
Because the integral of cosine is negative sine
Oh,
or sine, but the derivative is back to cosine.
okay.
So this part here will give us du, or cosine u, and we have this on the outside.
And then wouldn't you bring back the x squared?
Okay, well, remember u was x squared, so du is 2x.
Okay.
And you're right. So cosine x squared du dx would be 2x. So the answer would be 2x cosine x squared. Yeah, well, whenever you use substitution like that, yeah, use the chain rule because we're no longer in dy dx. We're now dy du dx. And D. Example 2, D. We have y equals the integral of 1 plus 3x squared for 1 over 2 plus e to the x, no, e to the t, dt.
So first you would flip the bounds and turn it negative.
Mm-hmm. Yes, because we have to have the x on the outermost. Well, yeah, before we do that, let's change the bounds. So we have negative 4, 1 plus 3x squared. So we have to do that first. It makes it much easier. Now we have to take a derivative of it. dy dx is equal to d dx of negative the integral of 4
The u substitution for the function or for the outer one or the
would we need it there? Would we need it there because we have e as our integral? Yeah, because we need to have this one has to be x. So let's make it. So therefore, du dx would be 6x. Yeah, that's. I was thinking, do we need to because we have e, but we do because it has to be a to x. So we change this 4 to u. Okay, so the negative goes out in front. And we have to have dy dx equals dy du du dx. So dy du, which would give us what?
would give us 1 over or well, you would have to bring that function on top, don't you? To make it a negative exponent on the whole thing.
And if you did that, all we have left on the bottom then would be the squared version of it. So, and then we have that on the very top as well. Because the integral, the derivative of e to t is e to the t. So the dm, this would be, so be the du would be so this would be okay. Now I have to change the u's and the x's. So that becomes u. Then we have dy du times du dx. Okay. So the integral and the derivative cancels out. So on this side, we have 1/2 plus e to the u. Times du dx. 1/2 plus eu. Times du dx, which is 6x. Which was negative 6x. 2 plus e to the power 1 plus 3x squared. That's the answer. Because these two, the derivative of the integral is just going to be this
Yeah, the inside function.
at u.
Mhm.
So we have 1/2 eu times du dx. Du dx, we calculated up here, was 6x. Yeah. Okay. Yeah, so it got pretty hairy there, but yeah, I started getting confused with all the x's, t's, and u's. But you're right. Once we converted this to u, we just treat this as 1/2 e to the u. Right. So now part 2 of the fundamental theorem of calculus. Tells us this. Integral of f of x dx from a to b is the difference of our function from a to b. And actually, there's something missing between here. We go from to that. And that's all it says. This is just a straightforward integral at the bounds, which is what example 3 tells us or shows us. And here's example 3. And remember, is f of x has to be continuous. F of x is cosine continuous?
Yeah.
Yes. Is secant tangent continuous? Yeah.
I can't, once we start getting into trig, I don't, I need a graphing calculator.
It's sine over cosine squared, which is sine over 1 minus sine squared. Can sine squared ever equal a -1?
Or sine squared? Are you talking about like, can sine squared equal
Which can't ever be, yeah, actually, this one here has
Mm-hmm.
asymptotes, so it's not continuous. It has asymptotes. It has asymptotes anywhere we have cosine. Anywhere cosine x equals 0, we have asymptotes, which is at pi over 2, 3 pi over 2, n pi over 2, as long as n is odd. This one here is continuous. This one's not at zero. So yeah, as long as it's continuous on the closed interval, we're doing okay. So we calculate several definite integrals using the evaluation theorem. That's the evaluation theorem. Rather than by taking the limits of Riemann sums. What are the limits of taking Riemann sums?
Wouldn't it be the fact that if it, no,
No, because Riemann sum, what it talked about there, since it is a sum, what we're looking at here is if we had a graph, a function between A and B, we would, the smaller these slivers we take,
the more accurate we
the
get.
more we get, and we add them all together. So the limit as x goes to zero, delta x goes to zero. That's what that's saying in the Riemann sum. So we're adding up all these small slivers as they get close to zero. Eventually we'll get the area of the curve. That's very tedious. So let's look at what we can do here. Cosine of x dx.
Mhm.
So what's the integral of cosine x?
Sine of x plus c.
No.
Oh,
Because we have
well,
a definite
yeah,
integral.
definitely. So yeah. And then sine of pi, well, you would do sine of pi minus sine of zero,
Right. Sine of pi is
1/0. Forget.
pi is where? Here's 0, pi over 2, pi. The sine value here is 0.
Oh, yeah, because
The sine is the y value.
yeah,
So it's 0 minus 0 is 0. All right. The next one we have b is the integral of from negative pi over 4 to 0 of secant x tangent x dx. You can use your cheat sheet here. The integral of secant tangent. If we work backwards, we know the derivative of secant is secant tangent.
yeah, which,
So
yeah.
this is secant. But yeah, definitely look on your cheat sheet, because now that once we've learned how to do it, we don't have to relearn the wheel. We just use the cheat sheets to figure out these things. So find the integral of secant tangent x, you get secant x.
Would the computer, let's say, again, because I'm not really good with trig, would it let you put that function or that, that in there?
How do you mean?
Like,
It's a final answer?
uh, yes, yes,
The final answer of this one is 0. And then for this one, we haven't calculated yet.
okay,
Yeah, because it's not going to ask you for the intermediary steps.
Mhm.
So it's going to give you the question, you work it out, and whatever you get for the answer, that's what you'll plug in there.
okay.
So secant is 1 over cosine. One over cosine negative pi over 4. Cosine of 0 is 1, so 1 over 1 is 1. And pi over 4 is square root of 2 over 2. It's going negative. Cosine is the x value. Negative pi over 4, the cosine is still positive. So it's going to be minus square root of 2 over 2, which makes it 2 over square root of 2. Rationalize it. We get 2 radical 2 over 2, radical 2. Yeah, you're going to look at, and pi over 4s are the easy ones. Because that's where the cosine and sine are both the same. They're both pi over square root of 2 over 2. All right. C. Example 3. C. We got the integral from 1 to 4. 3 over 2 radical x minus 4 over x squared dx. Okay. Let's work this out step by step. We can split these up. We can do 2 separate ones if you want, or we can keep them together. This is 3 over 2 x to the power 1/2 minus 4 x to the power negative 2. Actually, now we'll take the integral.
Yeah, they're saying,
So this first one, we have 3 over 2 x 1/2 plus 1 divided by 1/2 plus 1. Negative 2 plus 1, negative 2 plus 1. X to the 3/2. 3/2 over 3/2. 4x to the 1/2 over x negative 1 over negative 1. So we have 3/2 times 2 over 3, x to the 3/2 plus 4 over x these cancel, so we have x to the 3/2 plus 4 over x.
I was gonna ask, how did you get rid of the -1 at the bottom of 4x?
Negative cancels. 4 divided by 1 is 4.
Okay, I see.
That was an easy question. Thanks.
Yeah.
And that's a -1 exponent. The x is -1 exponent. It goes to the bottom. So let's look at this. We have 4 3/2 plus 4 over 4 minus 1 to the power 3/2 plus 4 over 1. So far, so good?
Mhm.
So first off, we got the square root of 4 is 2. 2 cubed is 8. 8 plus 1. 1 plus 4. 9 minus 5 equals 4. So the 4 to the 3 halves. That's the same thing as 4 to the power 1/2 cubed, which is square root of 4 cubed, 2 cubed, which is 8. That's where I got that from. So the answer is 4. And D. Oh, we have D and E. D is integral from 0 to 1, dx 1 plus x. Sure. And this is what we were talking about earlier today. So the integral of 0 to 1 dx x plus 1 remember that we talked about du over u equals ln absolute value of u.
Mhm.
The integral of it.
So just,
Well,
but by knowing it, it's, what is it again? Linear log, what is that? Linear log
Integral?
or natural log?
Natural log.
Natural log,
Yeah, ln.
okay. Natural log of x plus one, or x plus one, but that's under an absolute value.
Right. Because it can be, because we're saying that x can be anything. So absolute values. The derivative of that is 1. So we do have 1 over u. So the integral of this one is ln u from 0 to 1. So it's ln x plus 1 from 0 to 1, which makes it ln 1 plus 1 minus ln 0 plus 1. Since 2 is a constant, it can't do any of the absolute values anymore. So the ln2 is whatever that is. ln1 is 0. So the answer is ln2.
So it's ln one plus one, and then minus ln
0 plus 1.
0 plus one.
Yeah, exactly. So 1 plus 1 is 2. We don't need the absolute values anymore. E. Where's that? That one is integral of 0 to 1 dx x squared plus 1. So whenever you have a dx over some function, always see if it's du over u. The derivative of x squared plus 1 is 2x. No. So we have to look at our tables, integral tables. Do we have an integral table of x plus 1 on the bottom, 1 over x plus 1? Look at your charts.
Um, one over x squared plus one, or just the function, just having a function at the bottom?
Oh, yeah, one dx, one over x squared plus one.
Let's see.
I think I left all my tables at home.
You said common derivatives or integrals?
Integrals.
Okay,
Because yeah, we have to see, does this match with anything?
um. I don't see anything, or at least, I don't think I noticed anything.
Okay, if it's not just numeric, is there a trig function that matches it? The integral of one over x squared plus one.
I can't really see. I'm having a hard time seeing.
Number 18. Number 18. What number 18 says is this. The integral of 1 over a squared plus u squared equals 1 over a inverse tangent. It says something like that. But yeah, we look at so there's nothing on top. Look at the bottom. Look for the only one that has the sum of u is a function of x. So it's x squared plus a squared. That's the same thing. So this one becomes since a is 1, we don't have a coefficient. That's just 1. So it's inverse tangent of x from 0 to 1. Which is inverse tangent of 1 minus inverse tangent of 0. So inverse tangent, where at what value does sine over cosine, where does it equal to 1? At what angle? In other words, at what angle are the sine and cosines the same?
Um, Sine and cosines are the same at 45.
Or square root of 4 or 4, or pi over 4, right? Yeah, because at that angle, they're both the same. And when is tangent equal to 0?
How would you find that on the unit circle?
Well, the inverse tangent it works backwards. This is the y value. So at what x value will the answer be 0 for tangent? Tangent is sine over cosine. The only way that could be 0 is if the top is 0.
So sine has to equal 0.
So the x is 0, right? So inverse tangent of 0 is 0. So the answer is pi over 4. Yeah, and that's why I want to start this one, because we have to get our brains working back in this, even though this is not an assignment. It's just getting our brains working again.
Mhm.
The next section talks about the integral of a rate. The integral of a rate. So again, the integral of the derivative is equal to the function at b minus a. Which brings us to the net change theorem. The net change is a differentiable function f over an interval a to b, the closed interval. The integral of its rate of change is f of b minus f of a equals that. This is the derivative. Again, it's the same thing, it's just written backwards. Here, example 4 doesn't have anything to do, it's just explanations. If C of X is the cost of producing X units of certain commodity, then C prime is the marginal cost. Remember, anytime you have a derivative, that's called a marginal in business. If it's the revenue, it's the marginal revenue, the first derivative of it. The profit, the first derivative is marginal profit. So in business applications, that's what it means. So the integral from x1 to x2 of our marginal function is the cost of the second minus the cost of the first. It's the difference of the two costs. And if it's positive, we're increasing. If it's negative, we're losing money. Okay. And V, if an object with its position function s of t moves along the coordinate line, its velocity, remember how the position function is s of t. The velocity is the first derivative of the position function. The acceleration is the first derivative of the velocity, which is the second derivative of the position function. So if we're taking the integral of the velocity is made up of the position functions, so it's position st2 minus st1. It's the displacement over the time interval of those two position functions. Because the integral of velocity is the position function. So if we arrange the earlier function, what we had originally, f of b minus f of a equals the integral from a to b, first derivative. If we add f of a to both sides, we get the net change theorem formula. So let's look at example 5. Consider in our analysis of a heavy rock blown straight up from the ground by dynamite. That was an example earlier in this chapter. The velocity of the rock at any time t during the motion was given by the function v of t equals 160 minus 32t f sine of feet per second. So that's our function. And the reason it's negative, because 32 feet per second squared is gravity. So find the displacement of the rock during the time interval 0 to 8. Find the total distance traveled during this time period. All right, let's look at this equation. So example 5 gives us our velocity function of our rock flying straight up. A. Find the displacement of the rock during the time period 0 to 8. And then find the total distance traveled. During that period. Now, it says the displacement. It says here. So the integral of velocity is the displacement over the time interval. That's what we'll have to do. For the displacement, we're looking for the position of the object.
Mhm.
So what do we do?
Take the interval from 0 to 8 of the function.
Now from 0 to 8. Very good. So we get from 0 to 8 of 160 minus 32t dt. The integral of 160 is 160t. T to the power 1. So it's add 1 to the top and divide by that. So we get 160t minus 16t squared from 0 to 8. One 60 times 8, 16 times 8 squared minus 160 times 0, 16 times 0 squared. So that's going to be 0.
Over 8 minus it's 8 squared. 64.
And 24. Is it?
Not sure.
Yeah. So subtract these two because they're both powers of 2. This is 2 to the power 4. This is 2 to the power of 8. 2 to the power 6. So we get 2, 7, 256.
The way I do those large numbers is just dividing it into 2 different things. So 10 times, I'll do 10 times 64.
And that's exactly, that's what you're supposed to do. Yeah. That's the best
Okay.
way of doing it. That's the best way
I'm
to do it.
assuming other people get it quicker just because they do it often and.
No. It's actually, that's exactly how they do it. They break it into smaller chunks, and then it's much easier to add the numbers than to do all this carrying.
Yeah.
And so yeah, for the first one, we get 256. And for B, it's saying find the total distance traveled during the period. Well, this object went up and it's coming down. So for this one, we have to put our function in absolute values. Why put in absolute values? Because it doesn't matter if it's going up or down. We're looking for the distance traveled.
You wouldn't lose the absolute value once you take the integral?
No, because we find out at what point does it reach its vertex? Because remember, since our time period, this time, we start at 0, go to 8. We have to find out at what point do we reach our vertex? At what time t here? Because in this way, it's going positive. This way, it's going negative. So if we drop the absolute value sign, then for this side, let's say it's from 0 to c, we have f of x, or v of t. On this side, we have negative v of t from c to 8. So we can either keep the absolute value sign, but if we drop the absolute value sign, then we have to take the two separate intervals. And on this one, we have to change the bounds of integration. Instead of going from c to 8, we'd have to go from
8 to 4.
8 to c.
Oh, okay.
We have to switch this around,
Okay.
but it's going negative. So we have from 0 to 8 here. So at what point does it reach its maximum point of velocity?
When v of t is equal to 0? Or,
So, yeah, so first off, we take our function, set it equal to 0. Because remember, this is our velocity. At what point does the velocity equal 0? Because at its vertex, there is no velocity. So we have 160 equals 32t, divide by 32. T equals 5.
did you do minus 160 divided by negative 32?
I'll just move the 2 over there and then divide by 32.
Okay.
Or 32 times what is 160? That's easy. Okay. So we know that our two bounds of integration are going to be from 0 to 5. And then from 5 to 8. Okay, so this is the integral of 160 minus 32t.
Which we found earlier, didn't we? Yeah, we found that earlier.
Yeah, we found out as 160t minus 16t squared. Yeah, I'm just setting it up. Okay. So now from there. We know the integrals are 160t minus 16t squared. If I drop the absolute value signs, then I have to change that to a negative. Yeah. Because I haven't changed the bounds of direction, bounds of integration.
So instead of adding them, subtract them by each other?
Yeah, so if I was to add them, then I'd have to go from 8 to 5.
Okay,
And since I went ahead, it's much easier if I just kept it from 0 to 5, 5 to 8. I got to make sure I subtract them then. I change the sign of the second one. Okay, so here we get 160 times 5 minus 16 times 5 squared minus 0. One 60 times 8, 8 squared minus 160 times 5, 16 times 5 squared. See, it's not difficult, it's just a lot of writing.
yeah. Well,
0, 30, 80, 800.
I was gonna ask, um, is it the absolute, the brackets that you set up? You can't remove those at all, can't you?
We mean the brackets or the
Are those absolute values or brackets?
brackets? Because I have this equation that has a 5 minus 0 minus this equation,
Okay,
the second equation.
okay. Yeah, because I was gonna say you can cancel the other two out, but
No, as I was hoping, but we couldn't do that. Because this one and this one becomes a positive. So we'll be adding those equations. So this becomes 800 minus this first parenthesis becomes 8, 48, 1280, 16 times 64 minus 800 minus 16 times 25. Oop, no, I forgot that. I forgot to do this part. So that's going to be 800 minus 16 times 25 minus that. This is 400 minus 1280 2 minus 400. Should use calculators. No, I hate using them.
Yeah.
Okay, let me see. Check back up here. So it's 160 times 8, 16 times 64, minus 160 times 5, 16 times 25. 30 to 800. Okay. Eight is 0. 48. It's 112. Okay. So this one's correct. Minimum 960. 960. Okay, so that's 896. So it's 4, 8, 3, 384. 384 Let me try that. So I have 1280. 6 times is 36. Right, so it's 960. 960 plus 64. That's where I messed up. 960 plus 64. 1024. So 1280 minus 1024. 6, 5, 256. 256 minus 400 is negative 144. $544. Yeah, I just got brain this part here, I did it wrong. Everything else I got correct. I just messed up this part.
And that happens really often when it comes to like long equations.
Yeah, but I mean, I shouldn't have rushed myself. I should have slowed down. Because right here, when I did 6 times 16, I got 96. It was 960. That's in the tens column. And then I subtracted instead of adding these two. So again, it was my brain fart right there. All right, so the relationship between integration and differentiation. There. The relationship between integration and differentiation. They're inverses of each other. So the derivative of the integral is simply the operation which we learned earlier. And the integral of function is of a definite integral is simply the integral of the derivative back to the original function minus the at the bounds. The second bound minus the first bound. This is what we did at the beginning. So you see it, yeah. So the derivative of the integral is just going to be the function at the variable position. The integral of a derivative is simply the derivative, is just the integral of the derivative part. It's just the original function at the end bounds. And this was what I was saying earlier, the total area of an object, if it's below the curve, you'll have a negative area. If it's above the curve, you'll have a positive area. So in this one, if we were to look at the area from -2 to 2, if we took that, we'd get a negative area because the area is below the x-axis. We'd get x cubed over 3 minus 4x. Get 2 cubed over 3 minus 4 times 2 minus -2 cubed over 3 minus 4 times -2. 8/3 minus 8. -8/3 plus 8. So distribute those. We'd get 8/3 minus 8 plus 8/3 minus 8. Will give us 16/3 minus 16. Get a common denominator. 48/3. So we get -32/3. Or if we want to get a positive answer, we could take the negative of this, which would make it 4 minus x squared. So if you ever get a negative answer and an integral, that means it's below the x-axis. Number 6. Figure 521 shows the graph of that in its mirror image. The definite integral over the interval -2, and which that's what I just did. So there's the answer for this one. And for this one, we would take the integral from -2 to 2 of 4 minus x squared. So we get 4x minus x cubed over 3, from -2 to 2. 4 times 2 minus 4 times -2, -2 cubed over 3. 8 minus 8 cubed minus -8 plus 8 cubed. 8 minus 8 over 3 plus 8 minus 8/3. So we'd get 16 minus 16/3, which would give us 48/3 minus 16, 32/3, makes it positive. So that's all that shows us is if we're not sure, if we just take the function and we get a negative answer, this means that the function is below the x-axis. If we want to make it a positive function, then we change the bounds of integration. We can, to change it, we can either change that one to positive. We can either change the bounds of integration, or we can take the negative of the function. That's what this tells us. So if we have a function and it comes out negative, we either change the bounds of integration, that'll change the sign, or change the sign of the whole function, that'll change the sign. And the last page is example 7. What this one says, if you have an integral and it comes out to be 0, that means you have two halves that are equal in area above and below the x-axis. So this is the first one I talked about earlier. So the sine function from 0 to 2 pi. The definite integral over that will give us 0, because from 0 to 2 pi of sine x, integral of sine x is negative cosine x from 0 to 2 pi. So we have negative cosine 2 pi minus negative cosine of 0. 2 pi cosine is 1, plus cosine of 0 is 1, which makes it 0. So the area between the graph x above, the area between the graph f of x and the x-axis over this. The area between the graph and f of x and the x-axis over that interval. And that's essentially, if you want to find the total area, then we have to do two bounds from 0 to pi, and then from pi to 2 pi. Change the signs because this side is negative. So our total area is going to be 4. Find the area of the region between the x-axis and the graph, this. This will be our last one for the day. So example 8. So f of x equals x cubed minus x squared minus 2x. In the integral of -1 to 2. So what would be the first thing you want to do?
Um,
Because remember, this is a cubic function, which means it's going to look something like this. So we first find the x-intercepts. We can factor out an x. Because this one says we'll have three x-intercepts, three solutions. The signs are opposite because the second sign's a minus. The bigger number is going to be a negative. Now set each one of these to 0 and solve. Those will be our x-intercepts. So x equals 0, x equals 2, and x equals -1. Those are our x-intercepts. So we have those. We know that the leading coefficient is positive. It's an odd, so that means this side goes down, this side goes up. The graph crosses at each of these intervals. So between this function, our x-intercepts are at, oh, I'm sorry,
yeah,
at 0, -1, not 1. Yeah, because the x-intercept is there. So to find this integral, we have to go from -1 to 0, and then from 2 to 0. Or we could subtract it, or we can go from -1 to 0, minus 0 to 2. Because this part will give us a negative area. Okay, so I'll go ahead and do the first one. So we have integral from -1 to 0 of x cubed minus x squared minus 2x minus 2 to 0 dx. So the integrals is x to the 4th over 4, x cubed over 3 minus 2x squared over 2 minus, and I'll go in a second out, so those cancel. So it's going to be x squared. The integral of an exponential function, exponential number, is add 1 to the numerator and add something to the denominator. That's the rule. And that's why I just did it out. So add 1 to the top put the same number on the bottom, add one to the top. Put that. So what we have here, when x is 0, that's going to be 0. Minus 1/4, 1/3, minus 1. That's the first equation. That's that one. From 0 to 1. Minus 0 of all those going to be 0. Minus 2 to the 4th over 4, 2 cubed over 3, 2 squared. So it's negative 1/4 plus 1/3 plus 1. Minus 16/4 plus 8/3 minus or plus 4. So I distributed those. Distribute the negative in there. 16 divided by 4 is 4. 4's cancel. Negative 1/4 plus 1/3 plus 1 minus 8/3. Combine those two. Negative 1/4 plus 1 minus 7/3. The LCD is going to be 12. Three, 12, and 4. So it becomes negative 3, 12, and 28. Can't have a negative. There's something wrong there.
I think you screwed up all the way at the,
Now you're gonna tell me.
yeah, I mean,
So
I was confused. You had a negative on like that function, that 0 minus 1/4, or the parentheses 1/4 minus 1/3 minus 1. Wasn't it a negative 1 to 0? Because that's what I was confused at.
this was a negative.
Yeah.
I
So,
put ones in there, didn't I?
yeah, and so wouldn't it be negative 1 to the 4th? Or no, that
So
one,
this
that one
one-
stays there because it's a four, it's an even exponent, but the other one is a negative
This would
exponent.
be this would be a negative. So and that's a squared one, so that one stays there. So then that would become negative. Again, as I tell my students,
Yeah,
it's always a negative signs.
no, I was lost there, but I was like, maybe I'm not understanding something.
No, you're absolutely correct. But see, now this is gonna make it bigger negative though. Let me look at that one again. So I have x to the 4th over 4 minus x cubed over 3 minus x squared from negative 1 to 0 minus Same thing. So zeros aren't going to do anything. So I have a minus -1 to the 4th over 4 minus -1 cubed over 3 minus -1 squared. The 0 disappears. 2 to the 4th over 4. 2 to the 3rd over 3. 2 squared. -1/4. -1/3. -1. 16/4. 8/3. 4. -1/4. -1/3. +1. Okay, so these cancel. There, that's the sign that I messed up earlier. So we have -1/4 +1. So these two combine. 8 minus 1 is +7/3. So it's a -3. And this is 28.
37. Yeah, it was just the negatives.
Yeah. It's the negatives hosed me up. So that's it for today. I got your brains really hurting, didn't I?
Again, it's only difficult when it's great stuff and then when you're distributing negatives and stuff. That's, or at least when you're not keeping track of it, because what I tend to do